Welcome to this video about the Fourier series. This is an example of how I was able to use Mathematica in one of my future classes, and it should show you how useful Mathematica is and how you can utilize it further on in your career. So first, we got to talk about what a Fourier series is. A Fourier series is an addition of sine waves and cosine waves. Adding different sine waves and cosine waves gives us different shapes. So here I have a plot that is the sum of many sine waves and different cosine waves, and we're adjusting parameters in them. You can see that when you adjust these parameters, that the shape of the function looks very different. So if we want a specific shape that's repeating, then we can add different types of sine and cosine waves and get pretty close to this shape. So here's the definition of a Fourier series. There's different a terms. The a terms are times cosine, and there's different b terms times the sine. And we define our a terms and our b terms based off of these integral, where you're integrating over the period your function times a cosine or times a sine wave. So let's apply this. If we look at a function x of t equals t, that's essentially the function y equals x. So it has a slope of 1 and it goes through the origin. However, this is not a periodic function, and since we're adding sine and cosine waves, we need it to be periodic. So we will assume that every 1 second this period will be repeated. So it goes up, and then at the end of 1 second it goes up again. Every second it does that. Now the problem with this function is that at 1 second the value is both 1 and 0. Same at 2 seconds. So every second we have this jump in values where we can't take the derivative and we can't use it in scenarios that we would want to use it in. So let's define a Fourier series that approximates this function. So here we have a sub n and b sub n. So where a sub n is equal to, from 0 to 1, x of t. Right? We're integrating over the period our function times a cosine or times a sine, and then we get a value for a and a value for b, depending on what number of term we want it to be. Now we can use that function to define another function, which is going to be the Fourier series. So here I have a function f that takes n many terms and is a function of t. So you start with your first term, a0. We're calling upon the a sub n function. And then we're adding our a from 1 to n times the cosine of n times omega, all of that. Same with b. b from 1 to n times the sine terms. Now I can tell it the number of terms I want. So this is a function of 2 terms, and this is a function of 5 terms and 10 terms. And I can make a table of all my functions for the first 20 terms of the series. Now I can use these to tell how well my function approximates the original function we needed. So here we can see we have 1 term. This is the original function, and this is our approximation. So it follows somewhat, but it doesn't do the best job of following our original function. But if we increase the term, we can see that it's a little bit better. It starts following this line a little bit more. If we keep increasing the term, you'll see that it starts to get closer and closer to that function. So here we're at 4 terms, 5 terms. You can see 5 terms is pretty good. If you increase it all the way up, keep going to 16, you can see that it follows the line really well, except for at the end points where it has to jump down to the bottom. And that's the reason for doing this. It makes a smooth transition between the places where it wasn't continuous before. So we can use that in our differential equations and anything we might want to do with it. Increasing it up to 20 terms, you can see it still follows pretty closely, and it doesn't change that much from 16. So you can look at this function and see how many terms you actually need to get a good representation of the original function. So let's look at a system that we can apply this Fourier series that we just determined to. So here we have a mass spring damper, a mass connected to a wall by a spring and a damper, and we can pull it an initial displacement and watch what it does. So we can see we pulled it 1.5 and it moves back and forth. We can increase the mass and see how it has a slower response when the mass is bigger. And we can increase the stiffness, and you see when it has a bigger stiffness, it's faster. Bigger mass, it's slower. And if you increase damping on the system, then it basically just lessens these oscillations over time, so it'll come to a stop quicker. So that is if we pull it and then let it go and let it oscillate freely. But what if we had a force in there? So that's what we're going to be analyzing. So let's try that with the function that we have above. Now we have an equation, force equals mass times acceleration. And this should tell you right away we can't use the original function because you can't take the derivative. So we'll be using our force functions and analyzing the response of this system with a different damping and a different stiffness based off of the force series that we determined. So this, I'm doing mass times acceleration is equal to the force for two terms minus c times velocity minus k times position. And my initial position, my initial velocity are 0, and I'm solving this for position. So what this is doing, it gives me a function of time that shows me the movement of the mass if I have a force of two terms. This one below will give me a position, will give me a response if I put a force of 5 terms in there. So now I can take that and make these two graphs. The graph on the right shows us the force that we're putting in. So this is the force for 2 terms and the force for 5 terms. This is what we saw before, where it's trying to do that straight line, and the more terms it has, the better it gets. So blue is for 2 terms and yellow is for 5 terms. And here on the left, we have the response. So this is a graph showing where that mass is moving. It goes up and down and follows this shape. So if we look closer at that, you can see that the blue and the yellow, they have a little bit of a discrepancy right here for every time it repeats the function, but overall it follows the same path in general. So if this was our system, we wouldn't need much more than 2 terms because the response doesn't change very much. However, if we increase our stiffness, we can now see that the responses to this system is very different, right? So we have the same force as before being put in, but because our stiffness is increased, it responds more to these little fluctuations. So the response is wildly different between the two. And if we increase damping on the system, you can see that it has quite a different effect on it as well. So what does that mean in terms of our physical system? So if we look at the response of these two systems, the one on the right has 5 terms for the force, the one on the left has 2. The one on the left has 2 segments, so it pulls and then pulls again, where the one on the right has 5 terms, so it pulls 5 times. You can see 1, 2, 3, 4, 5 in returns. Now, if we increase the stiffness, you won't see as much movement in the masses, but there's still that hesitation. So this one still has 2, and the one on the right still has 5. And that means the responses, in compared to each other, are much more different than with low stiffness. So if we decrease the stiffness back down and increase the mass, we'll speed this animation up a little bit so you can see the response is essentially the same. So if you had a larger mass in the system, you might not need as many terms in your series, which might make the math and the computation a lot easier to do. So it's good to see how many terms you need in order to accurately display the force and how many terms you need in order to accurately show your system moving. So if we take a look at the code here, it's pretty messy and hard to understand. But essentially what I did was I took some of the code that Mathematica gives you. It gave you this mass spring damper, and I just used that to put my functions in there for position. A lot of this stuff though you see in class. You'll see the manipulate, show, graphics, there's a parametric plot, and especially up above, all the things that I did up here. You define a function, you take integrals, you make a table and manipulate things. These are all things that I learned in class. So it was really useful to be able to see what was going on and have Mathematica solve all of it, as opposed to the other way, which would be going into Simulink and making a function for each sine wave, and then adding those sine waves together to see the force, and then creating a system, and then putting the force through the system and turning on and off different sine waves. It was just a lot easier to do this in Mathematica. So there are definitely situations where Mathematica is a lot easier and better to work with and can provide a lot more functionality. So I hope this provides some inspiration to get to learn Mathematica more in your classes and to start to use it further on in your careers. Thanks for watching.